Hi, today we are going to talk about the medical images processing. The medical imaging is a process to create visual representation of the interior of the body. It has two functions: the clinical analysis, that are the X-ray, the magnetic resonance imaging, the tomography, and the ultrasound, and the medical intervention, like the endoscopy and the fluoroscopy. The quality of the images depends on three factors essentially, and these are the contrast, the resolution, and the noise. The contrast is the different luminances of color that makes an image. The contrast can be simply explained as the difference between maximum and minimum pixel intensity in an image. The contrast adjustment that depends on the difference in the signal average noise. The brightness can be defined by the amount of energy in the output by a source of light relative to the source that we are comparing. And the brightness can be controlled by the histogram. The contrast expansion, which is also called the histogram expansion, consists in finding the lowest and the highest values. For setting limits, we have like the lower limit that we assign a value of 0, and if we have a value in the higher limit, we assign a value of 255, so we can get a more balanced appearance. We call noise to the fluctuation of intensity of color that makes difficult to see what you want. It can be random or not random. For the random, it depends on the time and the replace. And for the not random, it's caused by the device themselves. Suddenly we see what we call a quantum spot, which happens by a random distribution of photons, and this spot decreases by increasing the time and repetitions. We have three different types of noises. The Gaussian, and in this type the average is 0. The dotted, which causes a lower spatial resolution, and the salt and pepper, that they are black and white pixels that causes an error in the memory, reconstruction, processing, and transmission. The reason signal noise, or SNR, is defined in the following way, where the average of intensity in the anatomy of interest is represented by mu s, sigma Vg is the standard deviation in tissue-free background. Now, the reason signal noise in differential mode is defined by the following way, where mu s is the average intensity in the anatomy of interest, or ROI, and sigma d is the standard deviation in the average intensity in the anatomy of interest of the image difference. I1 and I2 are the consecutive images without change in the parameters. And the S and R is different depending on the noise effect and visibility of the object. The contrast noise is represented by this formula, where sigma Vg is the standard deviation in background, mu A minus mu B is the difference of intensity between object and the background. Now, the spatial resolution refers to how much contrast can be found without a noise, and it can be found as black and white lines. The modulation transfer function is a magnitude response of the optical system to sinusoids of different spatial frequencies. When we analyze an optical system in the frequency domain, we consider the imaging of sine wave inputs rather than point objects. The sine wave target of various spatial frequencies are a linear shift invariant optical systems images of a sinusoid as another sinusoid. The limited spatial resolution of the optical system results in a decrease in the modulation depth m of the image relative to what we had in the object distribution. The modulation depth is defined as the amplitude of the irradiance variation divided by the bias level. The modulation depth decreases as it's going from object to image. The spread function. To study this parameter, we will consider the following example. A small circular hole is made in the center of a lead plate, which is located between the X-ray tube and a sensitive device for recording the image. An image of this board may register on a film or digital devices. By measuring the distribution of gray levels, is comparatively larger in the center of the image, where is located the hole, and decreases radially outward, decreasing to zero at some distance from the center. Ideally, if the whole circle is small enough and the imaging system is perfect, one would expect the display perfect circle within the image with a gray level equal therein and zero outside this. The size of the circle should be the same size as the hole in the lead plate magnification absence during the experiment. However, in the practice, this ideal image does not exist. By contrast, it appears one gray level distribution around the hole. The experiment shows that the circular image of the hole in the lead plate never has a good edge defined. The edge sharpness is lacking. If the hole is small enough, the shape of the distribution of gray levels is called point spread function or spread function of a point. In both cases, X-ray, the image can't be used for measuring the PSF of the system. Theoretically, the PSF is a useful concept in estimating the sharpness of an image. Experimentally, the PSF is difficult to measure due to the difficulties mentioned. To avoid this difficulty in determining PSF, the concept of the line spread function or line spread function LSF is introduced. For measuring the line spread function, we can reduce the technical difficulties associated with obtaining and measuring the point spread function. As its name suggests, the line spread function is obtained with an infinitesimal slit in an opaque object, rather than an infinitesimal point aperture. By replacing the circular hole by a long thin slit in the lead plate and repeat the experiment, the image formed on the receiver will be a line of a certain width with a distribution of gray levels are not uniform. The value of gray is high in the center of the line, decreasing toward both sides until it assumes the gray level of the background. The shape of this distribution is called line spread function. Theoretically, the line spread function can be considered as a set of orifices placed in each continuously side by side. Experimentally, the line spread function is much easier to measure than the PSF. Now, in the edge spread function, if a wedge is used with a single step such that half the area of the picture may be lit and the other air, then this new distribution of ray levels of the image is the edge spread function. For an ideal system, any cut made perpendicular to the central edge will produce a step function, like it's shown in the slide, where x is the direction perpendicular to the edge, x0 is the location of the edge, minus b and b are the limits of the image, and a is the constant. Mathematically, the LSF is the first derivative of the ESF. It can be seen that the ESF can be easily obtained experimentally due to the simple form of the plate required for the experiment we named before. Once the image has been obtained with the system, a cut is made perpendicular to the edge, obtaining the ESF. To calculate the LSF of the system must be bypassed the ESF. For the modulation transfer function, we have the system that is defined from the Fourier transform of the point spread function, and it's also possible to obtain the MTF, or the modulation transfer function, from the line spread function by taking the Fourier transform of the line spread function. If the slit is not a delta function with respect to the detector, then the MTF is obtained by dividing the Fourier transform of the line spread function by the Fourier transform of the object. Care must be taken, of course, where the Fourier transform of the slit is equals to 0. The relationship between the ESF, LSF, and MTF. The MTF response is called the high contrast image system because the pattern of even lines or edges source generating a high contrast phantom. For high contrast is meant that the medium used have high radiological contrast. To explain the relationship between these three parameters can be performed an experiment with a table evenly emit light, a non-translucent object placed thereon, and an imaging system that allows capturing an image of the configuration. From the image obtained in the ESF, perpendicular to the transition zone direction, this function is then derived and obtained the LSF, and finally, in the figure shown, MTF goes in the same direction. For the relation between contrast, noise, and resolution, we have these images, where we can see that the information extraction can be minor than the contrast. The spatial dimension can be minor than the spatial resolution, and the noise affects a lot the contrast and spatial resolution where it's lost. And that's all. Thank you very much.